Welcome back. Last class we learned about forces in general, and today we're going to start learning about different types of forces. So today we're going to look at both normal force and friction force. So let's start with normal force. Normal force is the force that prevents objects from passing through each other. So for example, if you have a table and you put a book on top of it, the book won't crash through the table and reach the ground. It'll stay there as it is. So let's see what's happening with a drawing. So we have a table, and we put a book on top of the table. So if we look at it from the side, we have the table and we have the book, right? But the book has a weight. The book is acting with the force of gravity on the table, downwards. And according to the third law of Newton that we saw last class, when the book pushes down on the table is pushing up on the book with exactly the same magnitude of the force, but in the opposite direction. So the book pushes down, that means that the table is pushing up on the book. So the two forces that act on a book that is just laying there in a table are the force of gravity, which we had called Fg, and the normal force, which we're going to call Fn. So basically what we have is that Fn is the force that prevents objects from passing through each other. So there is a condition that determines if there is normal force or not, and that is contact. If two surfaces are touching, there's always a normal force between them. If they're not touching, there can be no normal force. So if the book was above the table but not touching it, there's a space between them, there's no normal force, only when they're touching. So it's a contact force because it requires contact between two objects. And the direction, this is really important, is perpendicular to the surface. Actually, that is where normal force gets its name from. You might have heard that normal is another way to call perpendicular. So if we have the surface, our table for example, anything that is put above it will feel a normal force that is exactly upwards, perpendicular, so that there's a right angle between the surface and the normal force. That's what the perpendicular means. Now, the first thing people ask is always, what is the equation? What is the equation for normal force? And the answer is, it has no equation. So it has no specific equation, but we can usually figure it out because of Newton's second law, which I'm going to write here so that you guys don't forget. Newton's second law is force equals mass times acceleration. And by figuring out the acceleration, we can usually solve for normal force. So when there is just a book lying there, something lying on a surface, your phone on your desk, it's not moving. It's not moving at all. So its acceleration is 0. So at rest means that the acceleration equals 0. And if the acceleration is 0, m times 0 will be 0. So this means that the net force, the total force acting on the object, has to be 0. So we go back to our book over here. We have a book. For the net force to be 0, as we learned last class, the forces need to be balanced. So if there is, and there always is, the force of gravity acting on the book downwards, the force upwards has to be exactly the same size. So what does that mean? When the surface, when the table is horizontal, the normal force will always be equal to the force of gravity. So this is only for horizontal surfaces. In a couple of classes, we will learn about what happens when the surface is not horizontal. But for now, we will only care that the normal force for horizontal surfaces is equal to the weight, to the force of gravity, so that they cancel out and the object stays still. If the force of gravity was bigger than the normal force, there would be a net force down, and that would make the book crash through the table and reach the ground. If instead the normal force was bigger than the force of gravity, that there would be a resultant force or a net force upwards, so the book would fly upwards. Here it helps to remember that the force of gravity was defined as mass times g, which is 9.8. So we can say that for horizontal surfaces, the normal force is also mass times g, mass times 9.8. So you can keep that equation in mind, but that is not the general equation of normal force. That is only a consequence of Newton's second law when there is no acceleration and the object is in a horizontal surface. Now keep all of this in mind and we'll move on to friction forces. Okay, so now for friction force. Imagine you have a refrigerator, it's really heavy, and it's on the ground and you want to move it from one place in your kitchen to the other. So if you look at it from far away, you're going to see your refrigerator and the ground, and you want to move it, but you try and you see that it's really hard to push, and you don't understand why. Well, the truth is, if you look with a microscope here, the union between the ground and the refrigerator, you'll see that the bottom of the refrigerator is actually not that smooth. It has some spikes, and the ground is the same. As smooth as it might look, it actually has some spikes as well. You have to look at this with a microscope, but you'll find out that nothing, not even this board, which really seems smooth, nothing is completely smooth. Everything has microscopic points that make it rough. So what happens is that when you try to move the refrigerator, which is pressed together in the ground, the spikes of the refrigerator will get tied into the spikes of the ground, and it'll be really hard to move them because they're just like tied in together. That is what is called friction. So friction, we're going to call it FF. So this F is for friction and this F is for force, is the force due to the roughness of two objects in contact. So friction is actually another contact force. If two objects are not touching, there's no friction between them. And the harder pressed against each other they are, the harder it is to move them because the more friction there is. So there are actually two types of friction. So we have kinetic friction is one of the types, and we have static friction. Their names might give you a hint on what each one is about. Kinetic friction is when an object is moving. So this has to do with moving or sliding. While static friction is when an object is at rest. So you can always think, is the object moving? It's probably undergoing kinetic friction. Is the object not moving? It's probably undergoing static friction. So with the example of the refrigerator, maybe you've tried to push a refrigerator by yourself. You can push as hard as you can, but if it's big enough, you won't be able to move it. So even though you're pushing against it, you're actually making a force. There's a force that is opposing your motion completely, which is static friction, because you weren't able to make the refrigerator move. Yes, so if you push the refrigerator and it doesn't move, the force that is pushing back on you is static friction. Now, if you bring your friend over and the two of you push the refrigerator with all your force, and you're able to make it start sliding or moving across the ground, the friction that you're feeling is kinetic friction, right? So as soon as the object starts moving, the friction type changes from static friction to kinetic friction. So let's look at kinetic friction first. So kinetic friction is the force that slows down objects, and it's opposing the motion. So for example, if you're trying to move a box and you're pushing it to the right, and it's moving to the right, friction will be to the left. So always, 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 it's in the direction opposite of motion. And it's going to slow it down, of course. The more friction there is, the more it's going to decelerate. And this friction depends on two things. It depends on how hardly pressed together they are, and it depends on the type of material and how rough each object is. So this friction has an equation, and each of these things is put into the equation. So when we're talking about an object lying on the ground, for example, the how hardly pressed together is talking about the weight of the object. The heavier it is, the more it's going to push against the ground. The lighter it is, the less it pushes against the ground. So how hardly pressed together is actually given by this equation, by the normal force. So the more force the ground has to make on the object to push it up, the more hardly pressed together they are. So the normal force is going to be part of the equation for kinetic friction. And the types of material is actually put into something called the coefficient of kinetic friction. So let's write that down. The coefficient of kinetic friction is expressed as this Greek letter mu that looks sort of like a U but with a tail on each side, and the letter K to say that it's the kinetic friction. So a coefficient is always a number that is constant, but this one depends on the surfaces. So there can be a coefficient of kinetic friction between a refrigerator and a ceramic floor, and it can be 0.5. But if it's between a refrigerator and an ice floor, it's less because there's less friction between those two surfaces because of their type. So maybe it's 0.1. And maybe if you put rubber against rubber, it's going to be a lot greater, maybe 0.9. It's never more than 1. It's always between 0 and 1, and it expresses between two different objects how big that friction is. So using those two things, we have the equation for kinetic friction, which we'll call Fk, and that is equal to the normal force times the coefficient mu k. This is the equation for kinetic friction. So remember, if the surface is horizontal, we can use this equation for Fn, which means this Fn would be mg. So we would have Fk equals mg mu k. We'll do an example after I explain static friction. Now, static friction can be a little bit more confusing because it doesn't always have the exact same value given by the equation. So let's see what I mean. There is a floor and there is a box, and you want to move the box. What if you push just a little bit? The arrow is just this big. That's all you're pushing. It's not going to move because the box, let's say, is very heavy. So if it doesn't move, if it's at rest, that means there has to be a force that is opposing you that is exactly the same size as the force you did. So this we're going to call the applied force. We can put F apple for applied. And this force over here is going to be the static friction, because since the box is not moving, it can't be kinetic friction. So the static friction would be this size. But what if you push a little harder? If you push double that force, but it still doesn't move because it's very heavy, the static friction has to be exactly the same size. Notice that if the applied force was bigger, even a little bit, it would start moving to the right. But we said it's not moving yet. If the static friction was bigger, it would move to the left. Imagine you're pushing forward, but friction is making it move back. That just makes no sense. So it has to be exactly the same. So even if you push a little harder, but it's not moving, the static friction will be bigger. So the size of static friction is actually as much as it needs to be, unless it passes a maximum, and then it can't stop the motion anymore. If you push hard enough, if you push like this size, of course the static friction is not going to be able to be that big. So at that point it's going to move, and there's no longer static friction. Now there's kinetic friction, and we can use this equation to figure out the total amount of friction. So basically, when we give the equation for static friction, we're only giving the equation for the maximum static friction there can be. because as soon as it's bigger than that static friction, it's going to start moving. So our equation will actually be Fs max, because we're talking about the maximum static friction, but it's going to look just like the kinetic friction one. So of course it depends on normal force as well, how heavy that box is, and it depends on another coefficient, which is similar, but it's for static friction. So we have the coefficient of kinetic friction mu k, and we have the coefficient of static friction, and it's mu s. So they are different. Why? Because maybe you've noticed that if you're trying to push a refrigerator, it's really hard to get it to start moving. But as soon as it starts moving, it's a little easier to keep it in motion. So that means that the kinetic friction, mu k, is smaller than the static friction, mu s. It's easier to move something and keep it in motion than it is to move something that was at rest. So to overcome static friction is harder than to overcome kinetic friction. And finally, let's do a quick example. Okay, so we have this example. There is a 4-kilogram book lying on a table. So I'm going to put a 4 for the mass. And you apply a force of 10 newtons. So for example, there's a force to the right of 10 newtons. How much will it accelerate if the coefficient of kinetic friction, remember mu k is the coefficient of kinetic friction, is equal to 0.1. So since there is a coefficient of kinetic friction, there's going to be a friction force to the left, a friction force. And they tell us it will accelerate, so it has to be kinetic friction. So the first thing we need to do is calculate the kinetic friction. So we're going to use this equation, normal force times the coefficient of kinetic friction. The coefficient, we already have it, it's 0.1. And for the normal force, we can use this equation over here because the table is horizontal. So we do Fk is equal to, and Fn was m times g, and then we put the mu k. So we put in our values. The friction, the kinetic friction will be mass, which is 4, times g, which is always 9.8, times mu k, which is 0.1. And this will give us 3.92 newtons. So we actually figured out that this friction force over here is 3.92. And we're going to have to use Newton's second law, F net equals ma, to calculate the acceleration, which is what we're being asked for. So we need the net force. And we have two forces. So just like last class, we're going to figure out the net force by subtracting 10 to the right minus 3.92 to the left. This is going to give us a net force of 6.08 newtons. And now you can put this into that equation. So our equation is F net equals mass times acceleration. F net is 6.08. Our mass is 4, and acceleration is what we're trying to solve for. So to solve for acceleration, we pass the 4 to divide, and we get 6.08 over 4 equals a, which means that our acceleration is 1.52 meters per second squared. That would be the answer. So we figured out the acceleration of a box on a surface with friction using the equation for kinetic friction, the equation for normal force on a horizontal surface, and Newton's second law.